Hello, everyone. Welcome to the last day, that's the seventh day of African Women in GIS 7-day GIS for Beginners training course. My name is Sihana Williams, and I'll be taking over as a moderator for today from Nina. Due to personal reasons, she cannot join us, so I'll be taking her place to help us end the whole program. Once again, welcome. So for today, we'll be taking the last course, that's the last lesson, on Ndvi for vegetation, as well as watershed analysis. So this is a program that is going to end the whole course, and we thank you so much for joining us on this journey and being with us through from day 1 to day 7. Now, I would like to go over what we have done so far before we are joined by our tutor, that's Chidinma. From day 1, we had an introduction to GIS. We also further followed up with data types and how to acquire them, including the platforms for getting open source data. We looked a bit at familiarizing ourselves with the software that is QGIS, and we provided you details on how to download the software and also how to get familiar with it, as well as to know how to prepare yourselves for the continuing sessions. We took a look at geodatabase and also took a look at georeferencing, as well as digitizing and creating a map. We further took a look at how we had different analysis and applications for GIS, and we had a look at an introduction session to remote sensing, as well as image classification. Now, furthermore, we took a look at buffer analysis, as well as hotspot analysis, and taking a dive at land use and land cover, as well as modeling LST. Now, today, as I mentioned at first, we will be looking at watershed analysis, as well as Ndvi for vegetation. So thank you so much for joining us on this journey. We are so happy that you are benefiting. We have gotten a few comments and feedback, and we are so glad that we have been able to fulfill your expectations. And also would like to give a little shout out to everyone. Thank you for joining us. And also a reminder that you can still register for the course to get access to the assignment and also get your certificate of participation. So please do well to register if you have not been able to do so. We will be sharing the link soon. But if you have not, if you can't get access to the link, you can still go to our social media platforms. That's LinkedIn and Twitter to get access to the link. But I'm sure we will be sharing it very soon. So thank you for joining from Zimbabwe, Ghana, Kenya, South Africa, and Uganda. I'm sure we'll be joined with more people, and we thank you so much for joining us today. So without any further delay, I would like to give the platform to our first tutor for the day, Chidinma Omegu from Nigeria. Chidinma, are you ready?
Hello, thank you, Sihana. Good evening, everyone. Okay, before I will begin with the lecture for today, please do not forget to register for the training so you can be able to write the assignment and be given a certificate so that your efforts will not be in vain. So for today, we'll be having a class on watershed analysis using QSWAT. Yesterday, I asked us to download the QSWAT plugin from our QGIS plugin database. But before I go on, what is watershed analysis? Unfortunately, I wasn't able to do a PowerPoint, but I'm going to teach us using this one I downloaded from the website. So I don't even know the author, but I would like to acknowledge the author of this beautiful PowerPoint. But then, what is water watershed analysis? Most of us know about hydrological analysis cycle, that is the states in which water is being transferred from the atmosphere to the earth, then back to the atmosphere. We know that when it rains, we on earth intercept the rain in different ways via our water collectors. Vegetation as intercept it for their own uses. Then the rainfall is being used to recharge the aquifer. Then again, when you have high sunshine intensity, the sunlight helps in absorbing or reflecting back the water accumulated on the earth's surface back to the atmosphere, and the cycle goes on and on. So what is watershed analysis? Watershed analysis allows us to look at our environment, to trace out the water basins, the watershed, the flood basins, look at the flood plains, water basins, the sub basins, the water channels, and effects of man on these variables. We all know that one of the prevalent issues in the world now is urban flooding, and most often it is due to poor urban planning, and most often you find people building houses on floodplains. In a stable environment, in a stable ecosystem, you will find that you have trees growing around or alongside a river basin, a river channel. And the work of these trees are to absorb excess water from the river basin in cases of overflow. Overflow occurs in river basins when the input is greater than the capacity of the basin. For example, if a basin have a capacity of say 10 square kilometer, and the volume is, let's say, 2 cubic square meters, and when you have an input from rainfall that is more than the capacity of the river basin, overflow will occur. That means the excesses will be spilled into the nearby environment. So one of the reasons why we use GIS to analyze watershed is to map out these floodplains. Floodplains are where the rivers are defined as areas where the river have authority over, in a layman's term. And nobody has any right to build any settlement or construct anything that is damaging to the environment, that will form an obstacle to the floodplain, so that when we have an overflow from the river channel, the surrounding environment will not be affected. Rather, the vegetation around the floodplains should be able to absorb and curb the damages, thereby limiting adverse effects on the environment and on man. So using watershed analysis, urban planners use it to map out these floodplains and put out a law or a conjunction that nobody should construct anything there along these floodplains, thereby maintaining a natural boundary for man. Now, what are regional stressors, things that can affect urban watershed? We have sedimentation, mine drainage, acidic deposition, tissue contamination, the decrease in the riparian habitats. That's the trees or ecosystem found around river channels. Now, impacts of human activities include timber, mining, agriculture, stream alterations. Stream alterations mean creating an artificial channel for streams or for rivers, creating an alternative channels, but they are artificial. Because one thing about stream that a stream channel is above, it is something like the stream channel below. What is above is something like what is below, because below the stream, the open surface water, you have an underground water channel too, or network, obeying the law of the surface water. And it is the work of these channels to recharge the surface water. So when these surface water are rechanneled, it affects the underground flow or underground network. So when man alters the stream channel, it's altering the environment, it's altering the flow. And thus we keep having issues of flooding in the environment. Now, mining, of course, we know, affects the environment. Timber, reduction of vegetation around the rivers or river basin. Agriculture, still the same thing. When man doesn't obey the law of nature when cultivating, it affects the river channel. Now, this for the GIS database, I'm going to skip this. Skip this. Issues why we need to study watershed. So you can derive a relationship between the land cover runoff and receiving stream segments, track runoff from land to streams. You can see this. This is a river basin. This is a river channel, not a basin, sorry. This is a river channel. This is the watershed. That's the catchment area of this river. Thus, it gets its water from this neighboring environment. If you see this arrow, that's how this river is being recharged. And that same law applies underground too, below the surface. So when you know when you're able to delineate a watershed for a river channel, you'll be able to monitor the activities. You're able to monitor the land runoff from the land. You're able to monitor the recharge. You're able to monitor the outlets too. How this is the outlets where the water flows out from. Thus, there will be here is an upland or an uphill where the water gets its source from, but it is being maintained from recharges from the neighboring environments. So it is important that we monitor this watershed very well, because most of our food comes from agricultural activities going around the watershed. And when it is not properly managed, there will be a lot of food insecurities, there will be a lot of contamination, drainage water and water contamination, and there will be a lot of health issues too. Now, examples of scale differences. These are different types of watershed boundaries in an area. The green one is the main river. These tributaries of the rivers. The black boundary is the watershed or the river basin or the basin of this green river. So the previous methods of doing watershed analysis before the advent of GIS, we have using of topo maps and contour maps to delineate the water basins or the river basins. But though they are okay, but they're not so accurate, being that human error will come into play. This is an example of the manual method. If you can see this blue line, this is the river. This brown irregular line signifies the water, signifies the contour. Now, the red dotted line signifies the watershed. How was this derived? They derived it by looking at the corresponding elevation. They derive this watershed manually by looking at the corresponding elevation. Because you know that rivers flow from high elevation to a lower elevation. So to derive the river basin or watershed, this is a highland, this is a high elevation. So this is a plain. This here is a plain. So they derive the watershed by delineating the boundaries between the high elevation and the low elevation round the river channel. Rivers don't flow upland, they flow downwards. So the river will flow from a high elevation to a lower elevation. And rivers are found mostly within a plain, not on an island, not on a highland. So using the elevation points here, they were able to delineate the watershed of this river basin manually. But today, this is a sub-basin or sub-watershed of the same basin. But today we're going to look at using GIS to derive this. So due to time, I'm going to go straight to using GIS in watershed analysis. The data needs and how to explain the data needs. Like I said earlier, look at this picture here. Let me zoom in. Look at this picture here. Look at the picture. This is a valley, and these are highlands. So naturally, we should have a river flowing down in between these two mountains or between these high elevations. So this plain, there must be a river flowing through it. That's the law of nature, because these mountains accumulate water and there will be an outlet from them. And from these different outlets, you have a river flowing in between them. Now, for today's class, we will be looking at using QSWAT in QGIS to delineate watershed of an area. And yesterday, I asked us to go to our plugins, to download the SRTM downloader, because one of the major variable for watershed analysis is an SRTM data. That's a digital elevation model data. So for today, please search for SRTM downloader from your plugin, install it. When you're done installing, it will appear here, SRTM downloader. Now, another step to do is to add, let me remove this so you can see how I got it. Using the Quick Map Service plugin, I added the OSM standard map. Then I navigated to an area I want to work on today. Now this is somewhere in Nigeria. We have a lot of river channels. Yeah? So we're going to work here today. Now, the first thing I'm going to do again, the next thing I'm going to do again is to create my study area boundary. I did that yesterday. I went to my new shapefile layer, went to my folder, give it a name, SRTM. SRTM underscore ROI. Save is a polygon. You choose the geometric type polygon. You click OK. You can change the coordinate system, but I'm leaving mine like this. Click OK. Now, the next thing is to toggle editing and create the boundary of your study area. Click OK. Save your work, save your edits, save the project. Now, we need to download the SRTM of this particular location. Now, the next thing I'm going to do that, I'm going to locate my SRTM downloader for my plugin. I've installed it already, SRTM downloader. I'll click on it. Now, there are two ways to this. If you know your coordinates, you can input it here, or to be on the safe side, set canvas extent. Click on the set canvas extent. Now the coordinates have been inputted. Then output parts, please locate where you're going to save your work. Mine is on my documents, work, Hurray GIS, QSWAT. This is my folder, QSWAT. So I select QSWAT, select folder. I'm going to minimize so you can see what I'm doing. Now, once you've set this, you've set your parameters, set your output folder, download. Please make sure that this is loaded, is checked. Load images to QGIS, you download. Now, it will request for you to create have a login credential from Earth Data Login. I already have the credentials, so I'm going to log in. If you don't have it, please click on this and navigate to it, set up your, go to your website, to your web, your browser, and set up your login details. Okay. So when you're done, you go back again to here. I already have my credentials, so I'm going to click OK. Remember, we are downloading the SRTM. That is the digital elevation model provided by NASA, USGS. So allow it to download. Download complete. You close. Now, this is our study area, and this is the SRTM of the study area. The next thing I'm going to do is to clip out. I'm going to change the color so I can be able to see. The polygon very well. So the next thing I'm going to do is to clip it out. Clip out the SRTM using your study area to minimize the time you'll be using to run the analysis. Now, over here on your processing toolbox, how do I get here? For my processing, I'll go to toolbox. It brings me up here. Search for WAP. WAP. WAP under GDL raster projection. No. Sorry, I'm going to clip. Sorry. Not WAP yet. Clip. Raster extraction, GDL raster extraction. Clip raster by extent. Clip raster by extent. Click on it. Our input raster is our SRTM. Our clipping extent is our SRTM ROI. Leave everything as it is. Locate to your folder where you're going to save the work. Locate your folder, save to file. QSWAT, give it a name. Then save, then run. Close. So I'm going to look up it. We have already clipped out our SRTM using our processing extent. Please always remember to save your work. Now, the next thing we are going to do is to reproject, because QSWAT uses projected data for its analysis. It uses projected data for its analysis. Let me give you an example what I mean by projected data. Now, if you have already installed your QSWAT, please locate where your QSWAT is on your toolbar, SWAT, create new project. Am I too fast? Hello?
Chidinma.
Please, if I'm fast, please call me back so I can repeat what I said earlier.
Sure.
All right. So on the QSWAT plugin app, remember from your plugin, QSWAT, click on it. You should give you this menu. Click on create new project. Locate where your project is going to be and give the new name, SRTM, SRTM. Click on it, select folder, give your project a name, SRTM training. Okay. No. This is a new list altogether. So what they're going to do is click on delineate watershed. Delineate watershed. Click on it. Then navigate to where you have select them. Navigate to where you have your them on your folder. Go back. Come on QSWAT. So I have them here. Then say it here. So okay. You see, our DEM we downloaded is not projected, and it's telling us that DEM does not seem to be projected. Its units are unknown, so you cannot work with it. If you try to create a stream using this, it's going to tell you that it's not projected. You have to reproject it. This software or this app or this plugin only works projected data. Please make sure you project your data. So I'm going to cancel. No. Cancel, close, or yes, close, discard. So I'll navigate back again to my folder. It's where I have my QGIS. Oh, sorry. Oh, I can use here. Any questions so far, Sihana?
So we had one question that was asking for the instructions of installing the software plugin that you're using, but I have sent a link to help with that.
Okay.
Yeah, so far no other questions. Yeah,
All right. Thank you.
you're welcome.
Okay. So before we load our SRTM, our DEM into the QSWAT, we need to reproject the data. So back again to your processing toolbox, click on WAP, search for WAP. WAP means to reproject a raster data. Under GDL, you have raster projections, WAP, click on it. We're working on our input data is our DEM, this source CRS. We have use this pseudo, or you can use it default. Target optional. Now our target CRS is, we have to define our projected data. So click on this, select CRS, click on it, coordinate reference system, and select this, then search. For Nigeria and where I'm working for, the projected coordinate system I'm using, I'm going to use 32432. When I click on it, see, it falls, this is this red line, it falls exactly within the area I'm working. So this projected coordinate system is okay for me. I'll say okay, I'll click okay. Then leave everything as it is, scroll down where I'm going to save it, reprojected. I'll click on this, save to file. Then I'll name it them reprojected. Them underscore repro projected. Click save, then run. Our them is already reprojected, but we will not see the changes here because it is the only one that it is the only data that is reprojected here. So we're not going to see any changes in its coordinates here. But once we open up a new QGIS, the changes will be reflected. So I'll click on SWAT again, new project, create a folder, new SWAT. Okay, select folder, give it a name, then click OK, and allow it to load. Then click on delineate watershed again. Select them, navigate to your, click on these three buttons here, three dots here, navigate to your folder where you saved your SRTM. Remember, we're working with them reprojected. So click open. See. Remember that when, see the difference now, when we first loaded the one we downloaded straight without reprojecting it, it warned us that our data is not projected. And we couldn't run analysis with it. But now we have already reprojected our data and the plugin have accepted our data. Now we are going to run our analysis. First of all, we create a stream. Click on create streams. To create the stream within the DEM, within the area, I told you that wherever you have an elevation, there must be a stream. There must not a matter that must be a stream, but there will be some stream channels available there. Not in all areas, but it depends on where you're working on. And where we are working on here, we have a lot of stream channels. I've worked on this area before doing a project of mine. So I know that we have a lot of stream channels here. So we're going to create streams. Creating stream will show us the rivers present, the number of rivers present, and where they are. So click on create streams. Over here, I'm going to show you the progress of the work. Then allow it to load. Voila, our streams have been created. This is the stream network that are present in this environment. So you go back again, not this, to here. Using the inlet or outlet shapefile, I normally don't use it because it can be problematic. But if you are sure of your inlet, you have gone on field work, you are sure of where the water came in from, and you're sure of where the water is flowing out from, the inflow in and the outflow, inflow and outflow of the river, you can use this. But if you're not sure of it, please uncheck. Go straight to creating a watershed. But if you have the shapefile for this, or you're sure of the inlet, if you have the shapefile, you can use the shapefile. If you don't, you can use this to create the inlet yourself. The inlet is like adding dots. You create these outlets. You look for where the outlet is, add dots on it. Click on it to add the outlets and such. But if you're not so sure of it, just cancel. Don't add anything. Just cancel because it can be problematic. Discard. So I normally don't use this for inlet or outlet. I normally don't use it. What I do is to go straight after creating my stream, I go straight to creating the watershed. Now the water is going to give me the river basin boundary and the sub basins boundary. Like I showed us in this this a watershed bound. Okay, yeah, here is it. So this watershed that have been done manually here has been replicated here using GIS. So the red lines or boundaries we have seen here is the watershed or the sub basins of the river channels. So when you're done creating the river channel and you have gotten your water basin, it depends on what your work is on. You can stop here. But if you're going to look at the flood plains, maybe you are into urban planning, or you're in charge of the hydrological sector, I want to study the floodplains of these river basins, so that, for example, for urban planners, it will guide them in planning the area properly, so as not to go into the floodplain, to avoid urban flooding and such. So when you're done creating your watershed, come over to create landscape here. Create. Now over here we have different menus, buffer channels, dam inversion, branch length. But we're not going to work with this now. We are going straight to buffer channels. So what it does, use a channel buffer as a floodplain. So you can choose to increase it to say 30 meters around the river channel. Or you can say 100 meters. Depends. Sorry. You see, it says the width. So we're going to use 50. That is 50 meters on the both side of the river channel. So that anything that falls within that 50 meters is is entering into the floodplain and should be removed. If the artificial surfaces or artificial buildings or constructions, they should be removed. But if there are vegetations, they should allow them to remain where they are. But if it's a man's interference, that should be stopped or should be removed. So anything within that 50 meters buffer that is not natural should be removed. So within that 50 meters, nothing should be constructed around it. Nothing should be done around, and that is the floodplain or the flood catchment or the catchment plain of the river. Of the river. When you're done, you say great. After you're done setting your parameters, I use 50 here, you say great. Okay, you can see this white polygon here. When we are done with our analysis and with our parameters, you're going to say okay. Now, always remember to save your projects. Now we are done. So over here, from our layers, we have the streams, we have channels, we have sub basins, we have SWAT sub basin, we have upstream from inlets. But in this area, we don't have upstream from inlet. That's why we're not seeing any black boundary here. But we have the sub basins. Now over here we have our hillshade. That what gives it this this is the hillshade. It helps to make the elevation acquire the 3D look it has or the 2D look it has. Symbology, sorry. Then after the hillshade, we have the floodplains. That's for this river, for this blue river now, this is its floodplain. If there should be any building within this floodplain, it should be removed. Because if this river should overflow, that means the spread of the river overflow will reach to this extent. And this can also be used in monitoring flooding. When you create buffers around the stream channels, different buffers, can create another buffer here. We use say under create, we use say 60, say sorry 70. You create. So okay. Now we have both 50 buffer, 50 meters buffer and 70 meters buffer. This is 50 meters and this is 70 meters. This can be used as a guide when we have a flooding event to the extent the flooding went, the extent of the damage, the extent the river overflowed. This is one of the advantages of using this QSWAT to monitor your watershed or to carry out watershed analysis. help one to create the river buffer at various meters around the river channel. Now we have our dam, our elevation data. Oh, the numbers you're seeing here, we have 59 is the number assigned to the sub basins. Number assigned to the sub basins, and from here we have the highest we have is 53. That means we have 53 sub basins in this small area, and this is the major basin that collects this. This is the major basin. This is the main outlet. Hello.
Yes, thank you so much for that. We have one question. I just thought to let you of it since you are on the topic. So someone
Okay.
wants to know, does QGIS measure the buffer distance, example, 50 meters from the middle of the river or from the river banks?
From the middle of the river.
Okay, thank you for that.
Okay. So this is our dam, our digital elevation model. Let me check so you can clearly see our dam. Then if you want to verify the band, I was thinking it's going to show us, okay, this is the elevation value. Keep changing, and it is in meters. The white area, the white we are seeing here is a high elevation, and this is followed by this. This is a lower elevation or a low plane. So back to that, back again to this. Now over here you see, guys, you see river, the streams. These are the major streams, whereas you have channels. These channels can be ephemeral, that is, they are not permanent. They can dry up. Ephemeral streams, they are not permanent, but they can dry up. This is the major stream channel. This is the major river of the location, and this is its channels. You can see that these channels are like tributaries of the main river. Let me increase the symbol. Let me increase the width. So this is the main river, and these tiny blue ones are its tributaries, and basically most of them are ephemeral streams. That means during dry season over here in Nigeria, they tend to dry up. They tend to dry up. But the blue ones maintain the flow throughout the season. It might reduce, but you will still see river or water flowing through them. Now again, let me change it back. It's too big. Okay. Now, like I said earlier, this buffer helps to checkmate buildings, constructions in an urban area. It helps the town planners to put up a law that no one should build within 50 meters from the center, from the middle of the river. That in terms there should be any flooding occurrence, that the damages can be curtailed. That the damages can be curtailed. So in flood analysis, these are the basic basics one have to know. But as you go further and you want to run a complex analysis, maybe by creating HRAUs, that's hydrological response systems, that will help you to look at the effects of land use and soil, plants and urban build-ups on the floodplains. You can now go straight to using this. But for today, we're going to stop at the basic watershed analysis, that is deriving our watershed, creating the streams, and creating the floodplains using QSWAT. And that brings us to the end of today's class. Thank you.
Thank you very much, Chidinma, for giving us that intro session to the water analysis. So we'll be moving on to our next session. And we have Ndvi for vegetation. Now, would you help me to present Opeyemi, who will be coming to take us on that topic?
Hello, everyone.
Hello.
Hi.
Welcome.
Thank you, Sienna. Thank you
You're welcome.
for having me. Thank you, everyone, for joining. Good morning, afternoon, evening, wherever you are. It's evening here in Lagos, Nigeria, and I'm joining you from there. So I'll be taking us today on the final session of the 7 days masterclass. I'll be taking us in NDVI for vegetation. I have my slides here, so I think I'll just go ahead and share my screen so we can start from there.
Okay, can you please speak a bit louder? It seems you have a bit of static in the background, so it's a bit difficult to hear you.
Okay. I hope I'm heard now. Can you hear me properly now?
Okay, yeah.
Is it better?
Yeah, it's better now.
Okay, thank you.
Thank you, too.
So I'll be sharing my screen now. Okay, so I hope we can all see what I'm sharing. Okay, so welcome to the session on NDVI for vegetation. So basically, what we'll be going through today will be about the definition of NDVI, and in case we've not had any introduction to it before, it's a very important indices used in vegetation analysis and used in monitoring vegetation growth and development. So I'll be taking us through just a basic intro course and how to calculate NDVI using QGIS or QGIS. So please come along and I hope you learn a thing or two. NDVI for vegetation, basically, due to the application of remote sensing, the advent of remote sensing, and the benefits of it. One of the benefits of it to agriculture is the ability to remotely monitor large or small expanse of vegetation or agricultural land. effectively telling, the growth and development without actually going there physically, to study it. And that's one of the very cool things about remote sensing. So, application of remote sensing to agriculture is becoming more popular in recent times, with the increasing availability of free decision-ready satellite data. Initially in remote sensing, um, at the advent of remote sensing, data used to be very expensive and very hard to come by. But thanks to initiatives and development from NASA, from the European Space Agency, we have a lot of free data now available. So, with this data being available, there's increasing application of it to, everyday things, to improving our lives basically. So basically, there are a lot of indices used in addition to this decision-ready data, there are a lot of indices, powered by GIS that, we could use to monitor factors that affect um, crop and vegetation, among other things. And one of the most widely used and most widely applicable of these indices is Ndvi. So basically, NDVI, these are images, to just show like the RGB image shows a true color, representation of a field, of a vegetative field. And this picture shows a near infrared image of it, and as we move on, we will know what all this means. That this is the NDVI image. So basically, what is NDVI? The NDVI means Normalized Difference Vegetation Index. It is an index of photosynthetic activity going on in vegetation, and it's one of the most commonly used like VIs, as we've said. NDVI was created in 1973 when a research team at Texas A&M University studied data being back from the earliest Earth observation satellites orbiting Earth, and then it was Landsat 1, one of the earliest, satellites that was used for remote sensing. So, in 1973, then, remote sensing was quite novel, and this team they were able to map regional vegetation change across the growing season over a large expanse, and that was when remote sensing importance was being felt and it was being, studied and applied initially. So basically, NDVI measures the ratio of reflective difference in the red and near infrared portions of the electromagnetic spectrum to the sum of the red and near infrared reflectors. Well, that's a lot of English. So basically, what we are saying now is that NDVI is a measure of vegetation greenness, and basically it just takes the colors that vegetation reflects and it deducts it from the colors that it absorbs. Then it now divides that by an addition of the two. So it normalizes it basically. So basically what it does for us is it measures the vegetation greenness. As such, it represents a standardized way to measure a vegetation's health. It also allows for highly urbanized areas to be more easily identified. In a case where you are taking the imagery or satellite imagery of a large expanse of land that contains both urbanized and agricultural land, you will be able to detect what part of that image is actual vegetation and what part of it is urban land, based on even just this NDVI. Moving on, okay, so here we're just trying to I just want to introduce us to how important NDVI is and the things that make it work, which is the electromagnetic spectrum. Now, in our introduction to remote sensing, we were introduced to sensors and to satellites and satellite imagery, and we would understand that satellites usually take or capture data in the electromagnetic spectrum. I hope I'm not going too fast. I hope I'm with me. Um, Hello.
Yeah. Just take it a
Oh,
little slower, that's all.
okay. I'm sorry. Okay, thank you.
Oh, no
So,
worries.
So the electromagnetic spectrum then is central to us understanding plant health because basically, initially in remote sensing and even today, we understand that when we capture vegetation using satellite satellite sensors, we notice that vegetation or places that are highly vegetated and have healthy vegetation, they reflect near infrared and green colors. Green and red near infrared are reflected back and we can see them. It's unfortunate because if only we could see, normally when we see vegetation, we see it as green. Healthy vegetation, where chlorophyll is happening, for the photosynthesis is happening, we see that it's green. But it also reflects near infrared. Only that the human eye cannot see near infrared. If we could see it, we would see that green vegetation, healthy vegetation reflects both near infrared and green. So basically, what this NDVI now does is that it helps us to understand, based on the near infrared and green, how healthy the vegetation could be. Now, how the vegetation chlorophyll reflects more near infrared, like I said, and green compared to other wavelengths, but it absorbs red and blue light. So basically, the index takes the green and near infrared, and it subtracts the red bands or the red aspect of the electromagnetic spectrum, and then divides it by an addition of the two, therefore normalizing it. Now, we already have an idea of what spectral properties of certain satellite imagery. We are also aware of the different bands that a single imagery can have. For example, I know we were introduced to it in the beginning of this session, in the beginning of the masterclass. Landsat 8 has Landsat 8 data has 9 bands, while Sentinel-2 data has 13 bands. There are other sensors, but these ones are the ones that have the necessary bands or the wavelengths that we need for NDVI. Now, going on, these are like what I just mentioned now, which are the band classifications for both Landsat 8 and Sentinel-2 imagery. Now, how is NDVI calculated? Like I said earlier, NDVI takes the difference between the near infrared and the red aspects of the electromagnetic spectrum, and then divides it by the near infrared and red addition of the two, thereby normalizing it. So basically, we see that when the plants healthy vegetation absorbs red light and blue light, but it reflects green and near infrared. So when we now take a difference of, we take a difference of the red away from the near infrared. If we have high values, we know that the vegetation in that area is healthy. But when we have low values, we know that there's either no vegetation or there's dead vegetation there. So basically, that's what NDVI helps us to understand. Now, as it follows from the NDVI formula that we just said, and from what I've been saying, for Landsat 8 imagery, the near infrared bands and the red bands as stated here, Landsat 8 and Sentinel-2. For Landsat 8, the near infrared band is the band 5, while the red band is band 4. Sorry, there's a mistake there. It's band 4. Then for Sentinel-2, near infrared band is band 8, and the red band is band 4. So basically, when we are using QGIS or when we are using GIS software and we are dealing with satellite imagery and we want to calculate NDVI, basically what we know or what we need is the satellite imagery, basically, so that we can do the calculation like we said here. So basically, if I was in a GIS environment, I'll just basically take for example, I'm working with Landsat 8, I'll just take, the band 5, which is near infrared in Landsat 8. I'll put it here, and I'll just minus it I'll minus the red, which is band 4 in Landsat imagery, and I'll divide it and take the addition of both. I'll divide it by the addition of both. So it's basically it's pretty straightforward, and then it tells a whole lot about the vegetation as well. So how is NDVI calculated in QGIS? Okay, basically I just said that now. In QGIS, unfortunately, in QGIS, we have to use the raster calculator. In ArcGIS, I understand that there are algorithms that can just quickly tell you can just plug in, the band or the composite imagery, and it just tells you or gives you back the NDVI. But in QGIS, we have to use the raster calculator. So, but it's still pretty straightforward, and it's quite easy to calculate this. And I'll be taking us through that later in the session. Now, to calculate NDVI in QGIS, we use the raster calculator to subtract values of red band from near infrared band, then divide by the sum of the red and near infrared. All you need is the reflectance values of red and near infrared. Like I said, you just need the bands. That's all you need. You need your red band and your near infrared band, whatever satellite imaging you choose to use, either Sentinel or Landsat or any other one you choose or you have. All you need is just the red band and the near infrared, and you're good to go. Later in this session, like I said, I'll walk us through calculation of NDVI using Sentinel-2 imagery of Ikorodu, Lagos, Ikorodu, the local government in Lagos. So, okay, so basically I already did this and I just put it here. So basically, at the end of today's session, we should have an NDVI map similar to this. Interpreting NDVI values. Okay, so I've said a whole lot about what it is and how it's calculated. Now, how do we interpret it? NDVI values, we already said, it's a ratio, right? So the result of this ratio or this formula generates a value between -1 and +1. So it can never be below -1, and it can never be above +1. Basically, it's a ratio. The math gurus amongst us would already know why that is. If you have low reflectance or low values, for example, between -1 and 0 in the red channel, okay, if you have these low values, it means or it correlates to low NDVI values. And that means that it's usually either bare land, water, or dead vegetation, like I said earlier. So if you have low reflectance in the red channel and high reflectance in the near infrared channel, this will yield a high NDVI value and vice versa. So what this means now is that, when you have near infrared, high reflectance in the near infrared channel, that means that your vegetation is reflecting a high value of near infrared, and it means that photosynthesis is working actively. Chlorophyll is being used, and the plant is basically working the way it should, and it's high, it's growing fast, it's growing well. But when the reverse is the case, for example, in a vegetative land, you perform the NDVI and you see that some parts of it are reflecting, low NDVI values, while some parts are higher NDVI values. Then you can tell which part of that field is working, is growing well, it's green and vibrant, based on, the normal vegetative cycle, and what part of that land features, dead or dying plants, and you need to pay attention to them. Okay, so for example, when you have negative values, it's likely water. In this case, when you perform NDVI over a large expanse of land that also has water and also has bare land, this is what you get. For example, like this image that I have here, the green aspects obviously show like vegetation, but then these parts are not vegetation but built up areas. So for example, this area, it's a whole lot of, so it has, or it contains both bare land, both water, and both vegetation. So this red part, the part reflecting minus, it's water. It's basically water. So water always has this negative value of NDVI because basically water reflects blue and it absorbs near infrared. So it's the opposite of vegetation in NDVI. So it's on, if you have NDVI values close to +1, that's a high possibility that it's dense green leaves. But when NDVI is close to 0, there aren't green leaves, and it could even be urbanized areas, like I just showed us. NDVI values for live plants range between 0 to 1. Like I said, anything minus would either be bare land or water. 1 being the healthiest plants or crops, and 0 being the least healthy. A single value can be determined for every pixel in an image, ranging from an individual leaf to 500-acre field. So this is one of the very good things about NDVI. There's high precision. You can tell from, if from a single plant, you can tell from a large satellite image of a large area, you can tell how healthy a single portion, a tiny portion of the vegetative land is, as well as the big of the entire part. So it's highly precise. So moving on. Okay, this is an image here, and it basically depicts some of what we just said. On healthy vegetation, you have lower reflectance, or it will have lower near infrared reflectance or lower NDVI values, while high or healthy vegetation will reflect high NDVI values, basically. So importance and uses of NDVI. Like I said, it's a good implicator of vegetative health, and it is applicable and widely used in every aspect of vegetation and biodiversity study. Now we'll go on to talk about a few of the uses of NDVI. Okay, I'm also talking about, since NDVI is an indicator of greenness in vegetation, it has a high, strong correlation with green biomass. Hello?
Apparently, we are losing you a bit. Your background sound is a bit loud. It's covering up your voice.
Oh my God. I'm sorry about that. This is Nigeria. I had to turn on the gen. Okay,
Oh,
so
sorry.
yeah, so I don't know. I'll try to make it better.
Sure, that's fine. And also, can you hide the sharing screen? Let me your screen.
Oh,
Yeah,
I didn't
yeah.
know that.
Oh,
Does it
that's
sound
okay.
better now?
A bit better. Yeah, there's still a bit of background sound, but it's okay.
Okay. I don't know what to do about that. So I don't know. I'll just talk louder, and I hope you can get me.
Sure,
So,
you can speak closer to the mic too, so that we can hear
oh,
you clearly.
all right, all right, all right. Okay,
Thank
so
you.
okay, thank you so much for alerting me. So now, like I was saying, since NDVI is an indicator of greenness in vegetation and has a strong correlation with green biomass, a high NDVI value is indicative of growth, like as I said earlier. Now, importance and uses of NDVI. Precision agriculture for farmers. Now, the hello.
Apparently, please, the background sound. Hello everyone. Sorry about that. Apparently, I have muted you a bit. The background sound was a lot. It seems like you're at a place with a lot of people, so I'll soon add you again. Just let me know Once you have reached the quiet place, then we can continue. Okay, so I have unmuted you now. I think your background is okay now.
Okay. I really apologize for that. If I could get out of it, I would. So I'm sorry.
That's okay. No worries.
Yeah. So moving on now. I was talking about, okay, please let me quickly go back to what I was. My slides just zoomed out on me. Okay. So NDVI values are also known to have high correlation with crop yield. Remember, we are talking about the uses or importance of NDVI. Like I said, it's a good indicator of greenness in vegetation. And, greenness in vegetation also correlates with, growth, like normal growth, the way it should be in vegetation. And, normal growth and development also has to do with, crop yield. So for farmers now and agriculturalists that are more concerned with crop yield and, how much they can get from the little field that they have and the inputs that they are putting in, a good NDVI can tell them, can alert them about the expected yields that they hope to get from the plot of, a land or vegetative land, basically. So it's useful in measuring crop productivity and predicting future yield in crops. So other importances, or like basically the one of the importance for agriculture and for farmers, especially in precision agriculture. Precision agriculture comes about as as a result of adverts and advances in GIS and GPS and remote sensing. Using basically it's a fallout of using remotely sensed data as well as GIS technology, to improve vegetation efficiency or the efficiencies in crop yield and in crop cultivation. So it's basically using less inputs to achieve greater agricultural outputs through the application of modern information technologies. Now, precision agriculture, like I said, is facilitated largely by the advent of GIS and GPS and remote sensing technologies. And one of the major contributions of said technology is to the field of precision agriculture. And one of those things that, one of those important things that remote sensing has added is NDVI, basically. So the uses of NDVI in agriculture are limitless. However, I'll mention a few of them below, right here. So this NDVI can be used, for real-time crop monitoring, and especially over large expanse of land. The costs that would have taken, for large-scale farmers to physically go around their crop fields, is mitigated by the use of GIS and remote sensing. And they could also use NDVI, in this particular situation. So it's also good for crop yield estimation, for crop loss estimation also following a hazard. For example, in areas of the world where there are stuff like blizzards, overnight blizzards and hazards and the effects, the devastating effects that these things have on agricultural land. Using NDVI, we can quickly estimate in real time how much of a crop, of a cropland has been lost to hazards. And this is a very important aspect of disaster risk management and reduction as well. You know, NDVI also helps to guide fertilizer usage in croplands. So basically, when you calculate the NDVI for a field, and you're able to tell what parts of the field are green and doing well, and what parts are not doing so well. When you're able to get that, then you will know what parts of the field would require more fertilization or would require you to take a closer look to see what's going on there. So it's really good for precision agriculture for farmers. As well, conservation ecology. NDVI is very useful in the area of conservation and biodiversity. For conservationists that are worried about biodiversity and the loss of it through, natural hazards, man-made hazards and stuff, NDVI helps to understand how well or how much biodiversity is being lost or gained from man's activities and whatnot. So NDVI may be used to detect the distribution of biophysical parameters. The difference in vegetation types are primarily due to variation in soil, moisture, and temperature, which are key aspects of biodiversity. Further analysis of the exact relationship between vegetation type and NDVI might lead to the detection of variation in biophysical parameters from satellite imagery. Now, other aspects that NDVI can be very useful include, detecting spatial patterns of biodiversity in the sense of biodiversity identification and species richness. It also helps in grazing impact assessment, for when we're looking at the effect of, grazing on biodiversity also. We can also look at change detection. NDVI is useful in that as well. Vegetation or land cover classification, crop loss estimation, and, other things as well. So now, no index is truly foolproof. And some of these limitations that NDVI has will depend on what it's being used for. Now we're talking about the limitations of NDVI. Other vegetation indices have been developed based on NDVI and, the logic surrounding it. But this time adjusted for specific limitations that NDVI might have, such as atmospheric correction, soil background influences, and so on. Examples of these limitations, examples of the indices that have been developed include soil adjusted vegetation index, SAVI. I know we might be familiar with these terms as agriculturalists, maybe if there are any agriculturalists amongst us. These are also, developed based on the logic following NDVI. Enhanced vegetation index, EVI, perpendicular vegetation index, amongst others. Now, all these indices are also calculated using the same techniques, only slightly different formulas. So with a basic understanding of NDVI, you can comfortably calculate these other ones and use them as applicable. Now, let's move on to the QGIS tutorial on NDVI, like we were promised. I hope the slides didn't take too long. Now we'll go on into the proper tutorial on QGIS. Now, I sent in a data set earlier. I hope it was communicated to us so that we can download everything we need. Like I said, rather, all we need for calculating this is basically the red and near infrared bands of your satellite imagery, whichever one you want to use. Now, I personally chose to use Sentinel-2 data because of its high resolution. It's for Sentinel-2 data, we have as high as 10-meter resolution, which is what I'll be using here. The higher the resolution or the spectral resolution, the better your results, basically. For Landsat 8 data, I think the highest resolution is 30 meter, but I chose to use Sentinel because I feel that it's more it's more accurate based on the high resolution. So all we have here now is I just uploaded an XYZ tile, a base map basically from my XYZ tiles. I know we were introduced to this earlier in the tutorials. So basically that's what we see here at the background. Then this is my boundary for the local government I'll be working on, which is the Ikorodu local government in Lagos. So I basically just uploaded a shape file of the Ikorodu and I made it transparent so that we can see the background. Now, we're not using this particularly, but I'll just be using this, to delineate my study area, my focus area. So moving on now, firstly, what we need to do is to bring in our satellite imagery, the bands that we're talking about. So basically, they are raster bands, and I'll be bringing them in using the raster and the data source manager, the raster session under that. So basically, this is the data set that I sent in earlier. The 10-meter satellite imagery is right here. So I'll be taking the band 8 and the band 4 from this. So a quick way to do that is just I could take the two together and import them into my user interface. I'll just click on one, then control and click on the other, and I can bring in the two at the same time rather than doing one by one. That's a quick shortcut that I use. So I'll be adding that now. Right, so it's loaded onto the user interface already. We have here our band 4 and band 8. Like I already introduced us to, for Sentinel data, band 8 is the near infrared band, while the band 4 is the visible red band. And basically, the NDVI calculation, like we said, is just a division of the difference and the addition. So I'll be going on to my raster calculator to do this calculation, basically. So like I said, it's really straightforward. How do I get to the raster calculator? Let me show us once more. Go to the raster, from your data view, you go to the raster session or the raster drop down, and you have the raster calculator here. So once I click on that, this is where I get to. This is where it takes me to, basically the raster calculator. Now, it's just the way the algorithms, the formula is. Basically, we just take this. This calculator works. The calculator works basically like any calculator. So we have the operators here. I have my addition, subtraction, division, everything. So I'll just take my bands right here. They are my subjects. So I'll be taking them and putting them here. First of all, I want us to take note of something. It would be good to use parentheses. These brackets, they will be used to force our calculator to follow the appropriate process, the board mass process, because this formula uses plus, minus, and division. So we want to force the right order. So we use the parentheses. Now, so I'll be taking, like I said, my near infrared band first, then minus my red band, visible red band, which is band 4. Double click on that and you have it here. Then close bracket. Divided, the division, use the division operator here. Then open bracket again. Now, this time around, you don't need to take one, like the order doesn't really matter in this second parenthesis because it's addition. NIR plus R also equals R plus NIR. So basically we can, but I'll just stick to the normal order of things like I said. So I'll be taking my near infrared, then adding it to the red. Yeah. Then the next thing to do is to save it. Save it your output file. You could save it to any file of your choice on your desktop or on your computer. I'll be saving it right here, and I'll name it Ndvi 10 meter. So I'll be naming it. That's my Ndvi name. So basically, we just leave other we'll just leave all these others as default. We'll leave them as default and just, click OK to run the algorithm. First, I like to check to make sure that I didn't make a mistake. And I think everything is in order. So I'll just click OK. and I'll wait for a bit while QGIS calculates our algorithm. So let's just hold on a bit while we calculate that. Now, while this is running, I'll just go over like why I'm using this boundary. So basically, when you are calculating this, it will definitely be for a study or a study area or something. But I imputed this first so that I can focus. I can just, instead of going through or scrolling through my imagery, because it's actually a large imagery. Once this runs, I'll take us to the full extent of this imagery. It usually comes as a large imagery, so you know, you have to take cognizance of like your particular area. You have to take cognizance of that, and now zoom to a particular area that you actually want to work on. So it's still loading here. It's still working. It's a large file, so you still have to hold on to that. So I hope you understand why I brought in my shapefile first, so that I don't have to start scrolling through the imagery. If I had not done that, when I loaded this band, it would just take me to the full extent, and I'll not have to start looking through where my study area is supposed to be. But if you impute the boundary first, QGIS takes cognizance of that and just zooms to the layer that that you already have. So a few more seconds to minutes, and you'll have it right here. So it's pretty basic. It's pretty simple and straightforward. With this, you'll be able to do a lot of things. When you have your NGVI, it's a very good indicator, and it can be used for so many things. I hope you are with me. I hope I'm not lost or I've not lost somebody. I hope we're still here.
No worries, you're doing very well.
Okay, thank you, Sienna. So, just a moment. It's almost here. Oh, great. Here we have it. So I took it to the top so that we can see it. Now, like I said, I wanted to show us the full extent of this satellite image. So I'll just zoom to layer so that you can see the full extent. So basically, this is the full extent, right, of our satellite imagery, and this is our NDVI calculation. I know it looks boring now, but when we add colors and stuff, you'll see how beautiful it actually looks. So, okay, so I'm trying to bring my boundary up so that you can see what part of the satellite imagery is our study area. So basically, this is it. Zooming in, right? So what I like to do now is I would like to click this satellite because I don't need all of it. I just need just this part. So I'm just going to clip this satellite and the NDVI map to my study area, and I'm going to do this by using the raster extraction. So I'm going to clip raster by mask layer. I don't know if we were introduced to this initially, but if in case we were not, this basically just takes a raster and it clips it or it cuts it to the shape and the extent of the shape file that you have inputted. That's what this algorithm does. So I'll be clicking on it now. Okay, right. So basically, I'm just going to click my NDVI, my input layer will be NDVI 10 data resolution. My mask layer is already here populated. Basically, it's the only shapefile I have there, so it's there. Then, for the source CSR, target CSR, whatnot, I'm just to set this, I'm just going to keep the resolution of input raster And basically, it just takes everything from the input raster, which is the NDVI, the resolution, the everything. It takes it and just applies it to my output, basically. So I don't have to do all that. Then one last thing that I like to do is to set the no data value. Basically, you set this no data value so that QGIS can assign a value to other things that you are clipping away, which will be 0. So QGIS will add 0. There are other no data values that you can use. You can use -9999. So whichever one you want to, but make sure that it doesn't confuse the algorithm. So I'm going to save my output file as usual. I'll rather save it as to a file. So rather than to a temporary file. So I'm just going to name this clipped or clipped. Now my naming might not be very good in case you have like different data sets that you're working with. Okay, so the standard, or let me just do the standard, which will be naming it specifically. So I'll just say IKB, NDVI clip. So you usually want to name your files so that they don't confuse at the end of the day. Because if you are saving multiple data files to a single folder, it could get confusing. So you want to name it specifically. So I think we have everything in order. I'm just going to click one so that at the end of it, I have a clipped NDVI raster. Okay, great. So we have it here. So we have the clipped one here. So once we have it clipped, I'm going to put off every other one we have here, except my base map. I'm just going to put off every other layer that we have so that we can focus on our final map, which is the NDVI for ecology local government. So basically, you could at this point you could just take everything away, remove all layers. So you could just leave it if it's not confusing. So basically, what we have here is our NDVI, but it doesn't look or it doesn't tell us anything yet, right? It doesn't tell us anything yet. So what we need to do is we need to style it appropriately. So I like using you usually use the single band pseudo color for raster images. Basically, how did I get here? Sorry about that. I came to the style menu. This is the style panel. So once I've clicked on my NDVI that I want to style, I will click on the style, and this is where it goes to. You could also go through this way, properties, the symbology. It's basically the same thing, right? Just like using the style. So let me just go through this way then. Okay, so here we have it. So I'm going to be using single band pseudo color, which is what we use for styling raster images. And then we have, I'm just going to be changing my color ramp. I'll go through, change it to the red, yellow, green. This is mainly, in most cases, this is what people like to use to style NDVI and things like this, where the red represents areas with very low or -0 NDVI, while the green will represent the high NDVI values, right? So we could go here. I'm going to classify by equal interval, and I think let's just see how this is applied. Okay, great. Now that we've applied it, click OK. All right. So basically, like I said, I think this is looking very similar to what I showed us earlier. This is basically our NDVI for Hurray. See how easy that was and how useful it is. So basically, from the legend here, we can see that our lowest value NDVI is -0.37 stuff. And it represents basically the water area. Now, let me put this off so that you can see the satellite imagery beneath to confirm. So basically, this is the area of Ikorodu that is close to the Lagos Lagoon, which is basically a large water body. So that's the water body, and obviously it reflects very low NDVI figures in the minus. And also the this next one also reflects very, very low, right? And you can find these two colors in this area, on this part. Now let's understand better, what does this mean? What does this part of the map mean? Looking closely, let's look at, to understand better, I would like to introduce the land use land cover map for Ikorodu so that we can see better what these areas are, what these areas represent, right? And to confirm what we've been saying all along about NDVI. So the land use land cover map, I have one and it's in the data set already. I'm going to bring it in. It's a raster data. So I'll go to the data source manager again. And I'll be bringing in my land use land cover map. So, okay, so we have here land use land cover map, and let's close this so that we can see our land use land cover map. Okay, so we need to style it also. Let's take a look at, okay, let's take a look at the styling. Um, let's use the single band pseudo color as well. This time around, I'm going to style into 3 classes because this land use land cover map is actually three for three distinctions. It's basically supposed to be for vegetation, water, and vegetation, water, and built up areas. So basically, the vegetation here, I think I want to use color ramp that is more representative. So basically, one here stands for the vegetation. The number two stands for water bodies. That's this. And then number three stands for the built up area. So I'm just going to use a more representative color. So I'm just going to change my colors manually. I want for number one, which is red and which correlates to vegetation, I want a very good green. I want a very good green. Apply that. Ooh, it's looking weird, right? Let's change this. Number two means water, so I'm just going to put a very nice blue, right? Then for my green, which is representing the built up areas, I could choose to use light color, somehow maybe yellow, and brown. Okay, so I think it's a bit better now. So basically, so that I don't confuse us, let me just rename or let me let me relabel. Let me relabel. So this is vegetation. This represents water bodies, and this represents bare land or built up areas. Alright, so here we have it, the land use land cover map that we did, I arrived at this using maximum likelihood classification of the satellite imagery. I know we were introduced to image classification earlier, so I know we understand a bit of what that means. So basically, this is our land use land cover map, and I just wanted to show us how it correlates to our NDVI map and what we've been saying about NDVI. We've been saying that areas. Let me open it so that we can see what the classification is. Let me open it so we can see clearly. Okay, so like we've been saying all along, the red uh, correlates to very low NDVI values, so that's minus 0.3 and below. Or let's say this nice pitch also represents minus values. And we can see that we find them in areas that are built up, right? So basically the built up areas correlates to where we have the red or the peach. And the ones that the color that is very red, the lowest NDVI, can be found in the water body. Like we said, water usually reflects negative, very negative values of the NDVI. And like we see here, the water body correlates to where we find the lowest NDVIs. Right.
Okay. Opeyemi, please, we have a question,
Okay.
and
Okay.
we have
Please.
about less than 15 minutes more. So I'd just like to voice out this question. So someone would like to know how accurate is NDVI for vegetation analysis? He has follow-up questions, so after you answer this one, then I'll just add the others.
All right then. So basically, like I said, NDVI is very useful for vegetation analysis, but it's usually not used alone because it also has its limitations. And like I said in our slides, the limitations depend on what part of vegetation analysis you want to do. For example, one thing NDVI does is that it tells you how green vegetation is, but it doesn't tell you what causes it when the vegetation is not so good. So basically, what it does is it gives you an indication of the health of the vegetation, but it might not tell you the causes. So when you have that indication, you are now meant to go to that part and now find the underlying causes. And also, NDVI is, it's subject to certain limitations like atmospheric correction and atmospheric influences. Well, any remote sensing data has its limitations, and one of the major limitations is usually atmospheric limitations. For example, cloud cover and stuff. So you have to correct for these things. Also, there are other limitations like soil background influences. For example, when you are looking at vegetation from above and you are using the near infrared values, the underlying bare soil, for example, if the vegetation canopy is not so dense, the underlying soil, which does not reflect near infrared, might influence the values of your NDVI. So depending on the um, the status of your vegetation, maybe it's in the growth stage or in the maturity stage or in the harvest stage, depending on whatever part of the crop or whatever part of the vegetation, whatever phase it is in, then you have different limitations that might affect NDVI. But still, it's a very good index, and it should be used in addition to some others. And in a case where NDVI might not be useful or might not be as accurate for what you need it for, there are other indices that you can use, like I said, the SAVI and the EVI and others. So I hope I was able to answer your question.
Yeah, I guess so. And he has other questions. So the person would like to know what are the other, I think you mentioned this, but they would like to know what are the other vegetation spectral indices And what are the factors or conditions for adopting them? So I think you have touched on that in
Okay,
your
yes, I
answer.
think I did already. Okay, so
Uh, yeah, there's another question. They would like to know, can spectral indices like Ndvi, Nbui, Nbai, Mndwi be adopted for LULC? I think land use land cover classification.
okay, so what I'll say to that is, first of all, NDVI is not meant to be used for land use land cover classification. It can basically, what it's used for is to detect how healthy vegetation is. You know, there are other aspects of land use land cover, like bare soil, like, built up areas. So NDVI might not be used exactly for that, but it's just used to confirm. You can use it to confirm the classification that you've already done. So basically, like I did here, I just used it to confirm that my classification is correct or accurate. Usually, you do image classification using algorithms like maximum likelihood, other machine learning and AI algorithms. They are very useful for image classification, but it's not. You are not using NDVI specifically for image classification. You can use it to vet your image classification and make sure that you did the right thing, and you can use it in addition to image classification, to tell the vegetative status of a particular area. So basically, I hope I answered that question as well.
Thank you very much for that.
Okay, so if there'll be no other questions, I'll just round up. I think we're already at the end of the session, and I hope I was able to communicate, properly what NDVI does. Okay, lastly, let me just zoom in to this part of vegetation, the part that is vegetated, the part that we've already confirmed that represents vegetation in Korodu. And we'll see here that some areas of this vegetation are darker than some areas. Now, according to NDVI, these pixels all represent different vegetation status, the status of the different vegetation that they capture. So, like we can see here, this darker area would contain higher NDVI values, meaning healthier vegetation than this part of the image. So, like I was saying in precision agriculture, if I was a farmer and this was my land, I see that the vegetation here is doing very well. It's reflecting very high near infrared values, very high green. But here it's not so well. So it could be an indicator of whether the vegetation is healthy. It could be an indicator of the stage in the vegetation's life cycle, and other things like that. So this is basically what we use NDVI for, and and other areas of the image. Like I said, this is a built-up area. This is a whole local government. So obviously, these are the areas that are built up. And if you can look closely, you see that there are sections. You see that this is an urban area. So these are urban areas that are built up already. They have specks of vegetation also, like any urban area would have. And this can also be useful for temporal analysis of vegetation, like changes in vegetation. You could also use this, for example, to understand the urban expansion as well. How much of urbanization has affected the vegetation. For example, if I had this same algorithm, this same map, I think this image was taken in 2019 based on my data source. If I had, for example, something like this for 1980, I could just tell there will definitely be differences, and it will help me to tell how much of the vegetation area has reduced based on urban expansion, or how much of urban expansion has affected the vegetated areas. These are the things, these are part of the applications that you can use NDVI for. So with that, I would say we've come to the end of the session. The slides will be sent hopefully. And then, Sienna, thank you. African Women in GIS, thank you so much for the opportunity. I'm done.
Thank you too very much. Thank you very much. And we are happy to have learned something new from you. I hope everyone else learned because I did. And yeah, so would like to host or to kind of hold the closing ceremony for our little, in fact, our great initiative. That's to give people the opportunity to learn the foundation of GIS. This is an event that was hosted by the West African Zone of African Women in GIS, and it was part of their project for the month of July. I would like to take this opportunity to thank everybody in that zone who contributed and who helped us, especially the facilitators and all of you who watched this session. I hope you have benefited. Please share with us your testimonies or anything that you have learned. And please again, please pay attention to your emails. Those who have registered, you will be sent the assignments to work on and submit so that you can be eligible to get the certificate of participation. You will be getting that hopefully in the coming week. So please look out for that. And please do your assignment and submit it on time. Okay, so yes, thank you so much for joining us on our learning journey. In this session, we got to learn introduction to GIS, data types and how to acquire them, including platforms for open source data, familiarizing yourself with the software that is the QGIS software, as well as learning a bit on geodatabases. You got to learn a bit on georeferencing, digitizing, creating a map, as well as the different types of analysis and applications of GIS. We also looked at introduction to remote sensing and image classification, as well as a look at buffer analysis, hotspot analysis, and also land cover and land use analysis. We also looked at modeling LST and watershed analysis, that's the QSWAT, and Ndvi for vegetation. So I'd like to extend this thank you to all of you for joining us in our journey and to all facilitators for taking out the time and coming out to teach all of us. Now, these are some of the facilitators that came and I would like to acknowledge them. We have Oluwadamiliola, we have Chidinma Omiogu, we have Omonuola Akintola, we have Edna, we have Opeyemi, we have Nina, and she was the driver in this program. I'd like to acknowledge her, as well as Damilola and Susan. I'd like to thank all of them for helping us to make this program a success, and to all of you for joining us in this journey. On that note, I'd like to extend a welcome to all African women around the world who are in the geospatial industry or who are just interested in the geospatial industry to please go to our sites. We have a website, africanwomeningis.org, as well as our LinkedIn and Twitter pages to find the registration link to sign up. You will be sent a link to also register, and then you will be assigned a zone, and then you'll be joining our community. So we thank you so much for joining us, and we wish you a wonderful week ahead. And also, please submit your assignments so that you can get your certificate of participation. Thank you once again, everyone, and please enjoy your week.